morning, everybody. Today we're going to start Chapter 3 and we're looking at Section 1. We will be doing this section of notes in two parts. We're only going to go about halfway through and then we'll do the other part next week. Now, the main idea of Chapter 3 is, as you can see, is forces. We're going to be looking at all the different kinds of forces and how they affect motion. And the main idea of this first section is very important. It's that unbalanced forces change motion. So if you have an object that's moving along, if an unbalanced force acts on it, its motion will change. If you have an object at rest and an unbalanced force acts on it, its motion will change. Okay? So let's talk about what a force is first. Now, people a lot of times don't really understand what a force is. So we're going to try to learn today what a force is, how it acts. A force is a push or a pull, but just not any push or pull. It's a push or pull which causes motion to change or acceleration. It causes an acceleration. Could also be a deceleration since that's the same thing except you're slowing down instead of speeding up. Now, a force is also a vector quantity, so that means it has direction like velocity and acceleration and momentum. It has a direction as well as a numerical size, a value, okay? All right, now, suppose that you have more than one force acting on an object. Then we can talk about the net force acting on the object. The net force, which is symbolized with a capital F, just like force, but we put a subscript net on it to show that it is the sum, the addition of all the forces acting on the object of focus. So look at this example here. You have a big crate being pushed in various ways by people. So let's take a look. In this first one, both people are pushing in the same direction. Notice we are using red arrows to indicate the direction of the force, and the length of the arrow indicates the size of the force. So both of these people are pushing, let's say with a force of 8. We'll talk about the units later. So if they're both pushing with a force of 8 to the right, then 8 plus 8 is 16. The net force is 16. How about that? That's not so tough, is it? Now, suppose you have, and this almost looks like they're fighting, doesn't it? Okay, so let's suppose the girl is pushing with a force of 16 to the right, but the man is pushing with a force of 6 to the left. Now, if we take to the right to be positive, just like on a number line, then to the left can't also be positive, can it? It would have to be negative because opposite directions cannot have the same sign. So 16 plus a negative 6 means that the total force is 10, and that's what we call the net force. It is also 10 to the right because that was the biggest one. So the net force will also point to the right. Okay, look at the last one. These two girls are pushing on the crate. One is pushing with a force of 16 to the right. The other is pointing with a force of 16 to the left. So that would be negative 16 because of the direction. So 16 plus negative 16 is 0. The net force in this case is 0. So the crate goes nowhere. It doesn't move. But in these two cases, because you do have a net force, it's not being balanced like it is here. then in these two cases, the object will actually move, and it will move in the direction of the net force, okay? Objects will always move in the direction of the net force unless that net force is causing a deceleration, in which case the net force is opposite the motion. But in these two cases, the object will move to the right. Now, the SI unit, System International unit for force, is the Newton, named for Sir Isaac Newton, who we'll talk about in a few minutes, okay? Sir Isaac Newton was honored by having the unit of force named after him, okay? Now, let's talk about the 4 fundamental forces in the universe. There are 4 basic forces. We'll talk about how the forces are categorized in a few minutes, but the 4 basic fundamental forces, we do need to discuss these, if only briefly. The strong nuclear force is the first fundamental force. This is an extremely important force, guys. Without this force, the universe could not exist as we know it, because the strong nuclear force, well, let me give you a little lesson in the nucleus. As you know, in the nucleus of an atom, you have 2 particles. You have protons, okay? You have protons like this, and you also have neutrons. Now, I don't know if you remember from middle school, but protons in the nucleus are all positively charged. They have electric charge that is positive, okay? Neutrons are electrically neutral. They do not have net charge, but protons are all positively charged. Now, you may also remember that objects that have like charges repel each other. So what is preventing all of these protons in the nucleus of the atom? In fact, every atom everywhere, everything is made up of atoms, and they all have protons packed close together, and those protons are all positively charged, which means they're trying to repel each other. But yet they're not flying apart, are they? So what's making them stay together? It's the strong nuclear force that keeps the nucleus together. It's the glue that holds the universe together. It is even stronger than the electric repulsion between those protons. And if it weren't for this force, the universe couldn't exist. So the strong nuclear force, in fact, is the strongest of all the forces. It's the strongest of all the fundamental forces, and it keeps the nuclei of the atoms, let me put it down here, together. There we go. Keeps the nuclei together, keeps them from flying apart from that electric repulsion. And I'm sorry, my clock is chiming. We'll let it go through it. Okay, so now let's talk about the next strongest of the forces. That would be electromagnetic. Whoops, I didn't mean to do that. That's not a G. The G's coming up though. All right, there we go. That's an A now. All right, electromagnetic forces. Okay, these are the next strongest. And these are the electric forces between charged objects and magnetic forces, all right, and magnetic forces between poles, magnetic poles, okay, you know, like north and south poles, like on the Earth acts like it's got a giant bar magnet through the center. Now, it doesn't really have a giant bar magnet through the center, but it sure acts like it does, okay? So, electric forces, magnetic forces between poles. Electromagnetic forces are also responsible for keeping things from smushing through each other. For example, you're sitting on your chair right now. So what keeps the atoms of your rear end from smushing down through the atoms of the chair? What keeps you from ending up part of the chair? Well, the electromagnetic forces holding the molecules together, all right? They repel your molecules, so you don't smush through each other. That's kind of nice for us. All right, the next fundamental force are the weak nuclear forces. These are the next strongest. Yeah, even though they say weak. All right, so these are the next strongest. These are the strongest of all, then this, then this. All right, weak nuclear forces are actually, we don't really see much of that at our level. These are responsible for radioactive decay and radioactive changes within the nucleus. Okay? And lastly, the weakest of all of them, and you're going to be surprised, the weakest of all the fundamental forces is gravitational force. Gravitational force. And you may be thinking, but that's what keeps us stuck on the Earth. Gravity's really strong. It keeps us stuck on the Earth. Yeah, well, that may be true. But you know something? I can pick up a big old 50-pound bag of potatoes. I can exert my force on those potatoes against gravity. And guess what? The gravity is not that strong. Okay? If I can pick up those potatoes, the gravity is not that strong. So, gravitational forces, these are the weakest of all. And it's the attraction between masses. So, anything that's made up of mass has gravity associated with it, a gravitational attraction for other masses, always, okay? Think about this. You're sitting in your chair, and you may have another piece of furniture near you in the room, so how come your body just doesn't go from the attraction? Because it's so weak, all right? You don't move towards the piece of furniture and it doesn't move towards you because it's so weak. It doesn't overcome your inertia. It doesn't overcome the friction between you and the floor. And you've got to have a lot of mass to have a lot of gravity. Hence, we think of gravity as being really, really strong because you have to have a huge mass like a planet, the Earth, to see a lot of gravitational force, but it's still not that strong, okay? So gravity is the weakest of all the forces. All right, now, no matter what kind of force you're talking about, whether it's electromagnetic in nature, gravitational, nuclear, all forces can be categorized one of two ways. They're either contact forces, which means the objects must make physical contact. They must touch each other in order to exert the force. Or they're non-contact forces, which means they don't have to touch. They can, but they don't have to. The objects can exert forces over intervening distances. All right, let's think of some examples of both. Contact forces. Forces where the objects have to touch to exert the force. Well, those would be like applied forces from people and animals and machinery like a tractor or a tugboat. Those would be considered applied forces. All right, then there's also friction. You can't have friction without physical contact between surfaces. We'll be talking about friction in a few minutes too. Then there's also, a good example would be tension forces. Now, where in the world are tension forces found? Okay, tension forces are found in ropes and strings and cables and wires. If any of you play a stringed instrument or the piano, then you know something about tension. The tension in the wires are what help you play your instrument. They have different amounts of tension, which acts to create different tones when you play your instrument. Okay? Non-contact forces. Non-contact forces, remember, the objects can touch, but they don't have to, which is actually good for us. I would hate to think that the Earth would have to actually touch the moon to exert its gravity on the moon. That would not be too good for us. So gravity is a non-contact force. It can be exerted over an intervening distance. And that's another thing that's good for us. The sun keeps us going around it because of its gravity, and we don't have to touch the sun to have that exerted, or we'd be little vaporized critters, okay? Gravity is an example. Electric force is an example. And so is magnetic force between poles. And you're going to see examples of both electric and magnetic forces and how they work in some of your videos later. All right, so whether it's contact or non-contact, all right, forces are what change the motion of objects. And these are what we're going to be talking about. Now, for the rest of the notes that we are covering today, we're going to look at one force in particular, and that is friction force, which, as you know, is a contact force. So, friction. Now, friction also uses an F, but we put a little subscript F right there too, a lowercase f subscript. Friction, force. Little f for friction, big F for force. Friction force. And it is a force, oops, I see there's a typo there, a contact force. Get rid of the D on the word force right there, a contact force, which resists motion between surfaces. You know friction, right? Yeah, you know friction. When you rub surfaces together, you get friction. And as you know, a byproduct of friction is heat. The more friction there is, the hotter the surfaces get. Okay? Now, what causes friction? All right? Well, let's talk about it. When you look at two surfaces, those surfaces may seem very smooth and like there shouldn't be any friction or little friction, if any, at all. But if you go down and look at the surfaces on a microscopic level, you'll find they're not actually smooth. They have little points and little nooks and crannies. And when you're moving an object, those catch on each other as the surfaces are sliding against each other, and that resists the motion. You have to use force to overcome that. You have to push hard. All right? So this is the cause of friction. The fact that surfaces aren't actually totally smooth, but on a microscopic level, they are actually rough, okay? Now, when you have friction between two surfaces, the friction can actually be changed. So we need to see what does friction depend on? Two surfaces, like the crate and the floor, may have a different amount of friction than, say, two other surfaces, like a rubber mat being pulled across the floor. So what is it that friction depends on? Okay, how do you know when you're going to have more friction and when you're going to have less? Well, one very important thing that friction depends on is the force pressing the surfaces together. The force that's pressing the surfaces together. Now in physics, we call that normal force. But for our purposes, we'll just call it the pressing force. In fact, most of the time, the pressing force comes from the weight of the object pushing down on the surface. All right? In fact, the heavier the object, the heavier the object, I can't spell now, O-B-J-E-C-T, object, the more friction you will have. Or the more friction you get. So the heavier the object, the more friction you get, because a heavier object pushes the surfaces together more. In fact, you can see that yourself. If you put your hands together lightly and just rub like this, okay, there's not much friction, and you can tell because there's not much heat byproduct. But what if you take your hands and push them together? Ugh. Yeah, just do that. Oh my goodness, and then you really feel a lot of heat, and that tells you, oh, there's a lot of friction. So the greater the pressing force, the more friction you get, okay? Now, let's take a look at the next thing that friction depends on, okay? And that would be, let's get up here where we can see what we're writing. All right, that would be the roughness or smoothness, and depends on which way you want to say it, the roughness or smoothness of the surfaces in contact. Move it over a little so you can see. The roughness or the smoothness of the surfaces in contact. Think about it. Would you rather ride your bike on the pavement, or would you rather ride it on gravel? Yeah, I think we all know that. We would rather ride it on the pavement than on gravel, because gravel is so much rougher than the pavement. Okay? So the roughness or smoothness of the surfaces in contact. The rougher the surface, the more friction you get. The smoother the surface, the less friction. Okay, now, we're almost done here. There are 3 types of friction. All right, and let's talk about those quickly. You're going to learn more about these in some of the videos. The first is static friction. Now, static is actually a term that means stationary or at rest. So if an object is static, it's stationary. Now, what is static friction then? Well, static friction, excuse me, opposes the start of motion, or, oops, that's supposed to say or, not of. You can tell my word processor doesn't tell me a lot. Keeps something from moving. How many of you have ever had to help somebody push a broken down car off the road? Or maybe you've had to help your mom push a big piece of furniture aside so she could clean behind it or under it. then you know what I'm talking about. To start the big object moving, it takes a lot more force than to keep it moving once it is moving. That's because you have to overcome static friction, which opposes the start of motion. Okay? Static friction can also prevent motion as well. For example, a mover man, when he's unloading the moving truck and he sets a box on the ramp, the box doesn't slide down the ramp because static friction is bigger than the gravity that wants to slide it down. So it stays there, okay? Cars parked on an incline will stay there because static friction is greater than the gravity trying to pull the car down the hill. So, static friction opposes start of motion. Now, then we have kinetic friction. Now, you will find sometimes that people will call it sliding friction. So I'm going to put that right under here in parentheses. Sliding or kinetic friction. Kinetic is a term that just means moving, just like sliding means moving, except kinetic is the scientific term, okay? Kinetic friction opposes ongoing motion between surfaces. So once you've got an object moving, the surfaces are sliding against each other and you are overcoming kinetic friction to keep it moving. Another one that you see from time to time, well actually quite often, is rolling friction. Now, rolling friction is actually a special type of static friction. It's the type of friction that keeps wheels from sliding sideways on the road or balls from sliding instead of rolling. Now, if you've ever been bowling, you'll know what I'm talking about. Some bowlers can bowl a ball with such great speed that the ball doesn't even roll, it slides down the alleyway. When that happens, that means there is no rolling friction. There's just sliding or kinetic friction. And then some people, if you don't bowl it fast enough, some people, their balls will roll down the alleyway. That's when you see the rolling friction. Okay? When you bowl it really fast, you overcome the rolling friction, which again is a type of static friction, and the ball will slide instead of roll. For cars, that's not such a good thing because when you're riding down the road, you don't want your tires to slide on the pavement. You want them to roll, and you need that rolling friction to do that. Now, ways to reduce friction, all right? You can decrease the roughness by making things smoother. That would decrease friction, and I'm going to leave you to watch the videos on Friday to see some ways to do that. And you can also decrease the pressing force. Okay, and again, I'm going to, now I'll tell you an example right here. One way you can decrease the pressing force is to decrease the weight of the object being moved. If you decrease the weight of the object, then that makes the friction smaller and you can move the object easier. For example, if you're trying to move a big box of books but you can't push it because it's so heavy, then what you can do is take part of the books out of the box and move them in two goes instead of just one. So you can decrease the pressing force between the surfaces. Now, sometimes we want friction. In fact, there are a lot of instances where we want friction. If you surf, you know exactly what I mean. That's why surfers wax their boards. They don't want their feet to slip on the surfboard when they're surfing. So they increase the friction by waxing it. And that's what we mean when we say increase the roughness. Okay? Up north, they throw salt and sand on the roads in the wintertime to make them to increase the roughness and to melt the ice a little to make it easier to drive. Another way to increase friction is to increase the pressing force, just like we did with our hands. A way you can do that is increase the weight of the object. In the wintertime, up north on icy roads, people put sandbags in their cars to increase the weight of the car and thereby increasing the pressing force. And they're going to give you some other examples in the videos that you will watch in a couple of days. Okay? All right, well, that's it for friction. And I hope you've enjoyed it and learned some stuff. You're going to be learning some more stuff too, and I'm hoping next week we might even have a little mini lab on friction. You have a net force game tomorrow, so make sure tomorrow that you go back when you're doing the game and you look at this to get the idea of what's going on, okay? So you guys have a good day. See you soon. Bye-bye.